Okay, cool. Hi, everyone. I'm Ludwig. I'm currently still a PhD student at MIT, and I'll be a postdoc at UC Berkeley next. So you can already find me around the UC campus pretty often. And this is going to be a talk about joint work I did during my PhD with people at MIT mostly. So on the theoretical side, this is Chinmay Hegde, who was a postdoc at MIT, is now at Iowa State, and my advisor, Piotr Indyk. And then on the more applied side, this is a collaboration also with biologists at MIT. These are people in Ernst Frankel's lab, and Stephanie Gelke is also a computer science professor. Cool. Okay, so my access to graph problems here is more through the statistical side. And sort of the core problem this talk is really about is linear regression. So just to set up notation and make sure we're all on the same page, let's define this very sort of basic and sort of fundamental problem in statistics. So someone gives us a data matrix X. Say this is, for instance, house prices. Every house has a certain number of features, how many bedrooms, the location, and so on. And we want to predict for each house, as a function of these features, what is the price going to be. And then in many cases, as a first step, it makes sense to assume a linear model. So we can say we can write the prices Y as a product of our data matrix X and some unknown parameter vector theta star. And then there's some noise. This is always the case in statistical problems. And then the goal is, given our sort of a set of training data, sort of set of house prices that we know Y, and the data matrix X, how can we estimate these unknown parameters theta star? So like many good things in mathematics, this goes back to Gauss in the 1800s. And okay, so the question is, okay, what's new here? So we have this problem. We have a good statistical understanding of it for, I guess, almost 200 years now. Okay, so still, over the past decade, there has been a lot of work in high-dimensional statistics on extensions of linear regression. So in particular, different forms of constrained linear regression. So what is the main sort of thrust here? So now, in modern regression problems, you often have a data matrix that's fat, right? So here, I intentionally drew this so that the data matrix X is tall, in the sense that the number of data points that we have is larger than the 3 degrees in the parameter vector theta star. So basically, we have more data points than unknowns. And in that regime, linear regression works very well. But now in modern applications, you're often in a different regime, where the number of unknown parameters, here the dimension D, can be significantly larger than the number of observations that we have N. And then sort of classical theory tells you this is hopeless, right? This is an underdetermined linear system. Even if there's no noise, you can't solve this. But basically, we have many applications that fit into this framework, so we would still like to solve it. So one that I like a lot is magnetic resonance imaging. So you can explain this in the setup by saying the unknown vector theta star that we would like to sense is the picture of a patient, so say someone's spine. And then it turns out that the measurement setup in these MRI devices can be fairly accurately described as applying a subsampled Fourier matrix. So this is indeed a linear measurement setup. And now, basically, having a small number of observations N means that the person needs to spend less time in the MRI device. This can be very important, for instance, because children don't stay still for very long, and if you want a high-resolution scan, you should not move during your MRI. Okay, so what do you do? Like, typically what we do, if we want to solve a problem, and sort of the general theory doesn't tell you how to do that, we look for more structure in the problem. In particular, one thing that people have studied a lot in the past 10 years is how can you use sparsity in linear regression? The main idea is that the picture of the patient, say, that we want to sense, that we want to recover, is not just an arbitrarily random picture. In fact, there's a lot of structure. And one way to encode the structure is to say this picture of the spine here has a sparse representation, say, in a wavelet basis. Basically, this is the same reason why this image, you can compress it well as a JPEG. This means sort of that the inherent information content in this image is lower than the ambient dimension would suggest, and hence you can estimate it from a small number of linear observations. Good. So how do you do this? We say we want to solve linear regression with these constraints. Basically, sort of standard algorithm for standard regression is just least squares, right? We solve the least squares problem, and then we have a good statistical estimate. And now, if we want to do this with this additional sparsity constraint, the idea is simply we solve the same linear regression, same square objective function, but now with this additional constraint that the parameter vector theta should be sparse. So this is now not a convex problem because optimizing over sparse vectors is actually an NP-hard problem. But what people found out is that if you relax this to the L1 norm, so going from this non-convex L0 constraint to the convex L1 constraint, then this is a convex problem. We have now good algorithms for solving this, and this has very nice statistical properties. So this is also known as the lasso. I guess some of you have seen it before. Good, so to be precise, what is it that we get out at the end? This classical theory tells you if you want to have a good statistical estimate, the number of data points that you need should be at least the number of free parameters. And now if you have this additional sparsity constraint, you can get a significantly better sample complexity. So the number of data points that we need is only on the order of the sparsity, sort of the real information content, how many non-zeros are there in the unknown vector, times a logarithmic dependence on the ambient dimension. So if your sparsity is small, this can be a significantly smaller quantity, and hence you can get a good estimate from a small number of samples. I could go on now for a long time about many applications of this framework. Instead, there's a fun comparison you can do. So on the left here, we have Rob Tipshirani, who is a well-known statistics professor at Stanford, and he's particularly well-known for popularizing the lasso, so this L1 constraint least squares. And then on the right-hand side, we have Karl Marx, also a well-known figure, mostly known for popularizing communism. So what do the two have in common? Turns out they have almost the same number of citations on Google Scholar. So I guess this tells you something about the real-world impact of sort of sparse linear regression. I mean, it's obviously a silly comparison, but I think it's still nice to look at this. Good, and so once people realized that, okay, there's actually there are very good theoretical reasons why putting this L1 constraint makes sense and can help you statistically, people started introducing all sorts of constraints. So there's basically now a rich set of problems that we understand well from the statistical side. Sort of one line of work, there's sort of low-rank structure, like in matrix completion, how you can exploit that to improve your sample complexity. In signal processing, people use wavelets, and they give rise to tree structure, which you can also encode in your regression problem. In statistics, people have studied group variance of the lasso a lot. And then what we are going to talk about in this talk is graph sparsity. So this is an area I've worked on, and I think it fits the theme of the workshop very nicely. Okay, so what do you mean by graph sparsity? So now let's go to a concrete application. So this is in collaboration with the biology researchers at MIT. So they basically came to us and with the following problem. So they have a big data matrix, and big again in the sense that they have many, many features, but the number of observations here, this means the number of patients that they have in this data matrix, is actually not that large. Maybe tens of thousands of gene or protein expressions measured for a few hundred patients. And then what they also know for each of the patients is whether the patient has a certain disease or not. Okay, so far this is basically a regression problem where the graphs come in. So what they also have is that for many pairs of genes or pairs of proteins, they know whether there are known interactions between these proteins. And basically what they would like to find is a set of relevant proteins that can a small set of relevant proteins that can tell you whether a person has a certain disease or not, because then maybe if they do biological experiments after that, this would be an interesting thing to study. Okay, so if we have pairwise interactions between things, a very natural way to describe this is indeed as a graph. So we can think of the problem as basically we have a graph of our proteins. So every node here is a protein, and the edges encode whether two proteins interact. So it's a protein-protein interaction network. And based on this data matrix that we have, we would like to find a small subgraph in this large protein-protein interaction network that is highly predictive. So that basically just looking at the subgraph can tell you whether a person has a disease or not. And so here the graph structure is important for them because this allows, because it's biologically meaningful, right? If I give you a sparse solution and it's spread all over the graph, this might not be meaningful to them because they are really interested in something that could be biologically plausible. And if you have sort of proteins spread all over the graph but not connected, then it's unlikely that this is a sort of a real reaction pathway. But if you find a subgraph, then this could really be something that's maybe happening in a cell. Okay, good. So this is now exactly the problem we want to solve. Again, It's a linear regression problem. Maybe since we have binary features, it's logistic regression, but it doesn't really matter. So we want to find a parameter vector that is sparse and also obeys this graph constraint. Good. So, okay. So this is the problem setup. Are there any questions so far? Feel free to interrupt me. Good. Okay. So the question is now, how do we formalize this problem? Again, we want to solve just as before with sparse linear regression. We kept the least squares loss. We're also going to keep the least squares loss now. And we'll add a different constraint. So instead of this L1 norm constraint, now we add the constraint that the parameter vector theta that we want to find lives in this constraint set, which basically encodes that the vector is sparse and the sparsity pattern obeys our graph constraint. Good. So now, natural question is, how do we solve this? And sort of, if you have an optimization background, of course, the first guess for solving these problems is always gradient descent, right? I mean, okay, the objective term here is nicely convex in theta, so this is a good idea. One catch is that the set C is actually now convex, but this is okay in these problems. We understand fairly well now, theoretically, that optimizing over non-convex sets in these problems is okay. Then the first method for optimizing sort of over constraint set is projected gradient descent. So in case you haven't seen this before, so basically just like gradient descent, this is an iterative method. So in every iteration, we first compute a gradient and then take the gradient step. But now the problem is we don't really want to find an unconstrained solution, but we want to find a solution in our constrained region C. And now, in order to make sure that we always stay in our constrained region, we just project back. So we take our gradient step, and then we assume we have access to a projection operator P, which takes an arbitrary point as input and sends it back to the closest point in the constraint set. Okay? And then we just repeat. So now we have made some progress in our objective function. We are still in our constraint set because we projected. And then we do this again, compute gradient, project back, compute gradient, project back, and so on, until we've reached some convergence criterion. Good. I mean, so far so good. So computing gradients in these problems is typically very cheap. You just need to look at your data matrix. The real bottleneck is computing projection. Okay, so we need to come up with an algorithm that takes as input an arbitrary point and gives us the best approximation in this graph sparse set. Okay, well, this is good as an algorithmist. Okay, we know a lot about graph problems. Maybe we can do this. Okay, so let's sort of think about exactly what is the problem that we want to solve here. So basically, in order to solve this graph sparse projection problem, we need to solve the following task. So someone gives you a graph with node weights. These come from gradient descent. And then sort of two constraints. So we want to find a forest, so a set of trees, so that the number of trees in the forest is at most a given number. This is G here, say 2. And the total number of nodes that we pick up is at most the sparsity S. Okay, so for this problem here, if we have these node weights, this would be the optimal solution. It's 2 connected components, total cardinality 3. And if I sum up the node values, then I get the maximum I can get with these constraints. This would not be a solution. The total number of node values is larger, but here we have 3 connected components, so that's bad. We want to find the best thing with only 2 connected components and 3 nodes. Good, so you can think about this for a little while, and then you realize, bad news, this is actually an NP-hard problem. So basically, projecting onto the set of graph sparse vectors is something we probably can't do in polynomial time. Okay, there are different ways around this now. We could say, okay, let's maybe come up with a heuristic, but we were trying to come up with an algorithm that we sort of can prove end to end. And sort of one natural idea that often helps a lot in algorithm design is if you can't solve a problem exactly, maybe you can come up with a good approximate solution. An approximate here in the sense that you can actually prove that, say, the solution is always within a factor of 2 of the best possible solution. And so if this is exactly what we did, so this is actually somewhat earlier work that we did. So here we introduced the notion of an approximate projection. So this is the definition of a projection. So we have our set C, the set of graph sparse vectors. And now you give me a point P, which can be arbitrary, doesn't have to be in the set C. And we want to find the best approximation in our constraint set. So basically, I want to find a point Q in the constraint set so that the distance between P and Q here is the smallest possible distance I can achieve with a point in the constraint set. Okay, and then to make this approximate, we just add a approximation factor CT here. So think a factor 2. We want to find a point which is within factor 2 of the best possible projection. Good. And so this is a good first step because you can do this for graph sparsity. The problem is this is both for the optimization experts in the room. If you want to make this a nice provable algorithm, this is not going to work. In fact, I can prove to you that projected gradient descent is going to fail for any approximation ratio greater than 1. So even if you can approximate this very well, say 1.001 approximation ratio, for large enough problems, I can still construct an instance and an approximate projection oracle satisfying this guarantee that will make gradient descent basically end up in an infinite loop where it does not converge. Okay, so initially we thought, okay, that's not great. But then it turns out if you use more approximation, you can actually make this work. So without going into the details on the optimization side here, just to give you a sense of what's going on, basically you need a second complementary type of an approximate projection. And here the idea is that you want to find a vector in your constraint set which maximizes the inner product with the given input. So for exact projections, these two notions are exactly the same. But once you allow approximations, these two are actually different. So in the sense, this is like approximation problems for minimization and maximization problems can often have quite complementary guarantees. It's the same here with these projections. And then what we showed in earlier work is if you can solve both the head and the tail approximation with a constant factor approximation, then projected gradient descent works. Okay, this is good. So now we can go back to our graph sparsity problem and see if we can come up with these approximate projections. And the answer is yes. So there's obviously a very rich history of approximation algorithms for graphs in theoretical computer science. And the main inspiration here comes from types of Steiner tree problems. So let's start with the basic Steiner tree problem. So this is the following. Someone gives us a graph with a certain set of terminal nodes. Here the red nodes are the important nodes that we want to connect. And we want to connect them in the cheapest possible way. Basically, every edge has a certain cost. And this would be the cheapest possible solution to connect the red nodes. Good. So this is a very well-studied problem. This is also the reason why this exact projection is NP hard, because Steiner trees are NP hard. But there's a lot of work on approximation algorithms for Steiner trees. Okay. This is not quite enough for what we want. So we want we work with a generalized version of Steiner trees. And this is the following problem. So this is the graph theoretic or graph algorithmic core of this work here. This is and people have proposed this before. We make use of it. This is the so-called price collecting Steiner tree problem. Okay, how does this work? So now we don't have a fixed set of terminal nodes that we must connect. Instead, every node has a certain price. This is the price P here. And the idea is that now there's this trade-off. Either we connect a node and we get its price, but then we have to pay the connection cost, or we just leave out a node from our solution, but then we have to pay this price. So the overall objective function is the following, and we want to find a subtree T that minimizes the sum. So for all the nodes that we don't include in our solution, we pay its price. So think of these really as penalties for not connecting nodes. And then for all the edges in our tree that we use to connect things, we pay the corresponding edge cost. Okay? So this is strictly harder than the standard Steiner tree problem. You can encode this into price collecting Steiner trees, but you can still have good approximations for this. So in particular, in a very nice algorithm, first of all, this is the example solution for this problem here. So this would be the optimal subtree. And say that connecting the node 3 wouldn't make sense because we only get 3 less penalty, but we have to pay 9 for the edge. Okay, and for this objective function, there's a very nice approximation scheme by Gulmans and Williamson. So sometimes when I give this talk in front of theoretical computer scientists, they now get confused because they see Gulmans-Williamson and they think SDP rounding, like semi-definite programming rounding, like for maxcut. This is a different approximation algorithm. So the two did a lot of great work together, and they introduced this approximation algorithm for a lot of price collecting type problems. And sort of what we did in our work was use this as a starting point to generalize this in a variety of ways. So first, basically, we generalized this from working only for individual trees, finding a single tree. We want to find forests, so basically sets of multiple trees that still have the same approximation ratio. So you can do this. I don't think we have time to go into the details for this, but I really encourage you to look up this algorithm. This is one of my sort of favorite combinatorial graph algorithms.
Sorry, can I ask a
Yes.
question about the previous slide?
Yes.
So when you're trying to find the tree,
Yes.
you're trying to minimize like the sum of other positive quantities?
Yeah, so we try to minimize the penalties for the things we are not picking up. So just the empty tree would not be a good solution because then I pay penalties for all the nodes. Right? So the sum is over vertices, not in the tree. Okay? Yeah, this is a bit confusing because they're called prices, but in the formulations they're more like penalties. Good question, thanks. Okay, and then so the initial work by Gilmans and Williamson was a polynomial time algorithm. We want this to run on large graphs, so we developed a nearly linear time and practical algorithm. We will see running times later. And then basically, sort of with this machinery for price collecting Steiner forest, you can reduce the graph sparse projection problem to a sequence of carefully tuned price collecting Steiner forest instances. So again, we don't have time for the details here, but basically you can introduce this Lagrange parameter. It's not really Lagrange because it's not really convex, but so the idea is the same. And then when you do a binary search over this trade-off parameter between node prices and edge costs, you can prove in the end you get out an approximation guarantee for the graph projection problem. You get actually both out of this. So tail you get out of this fairly directly. For head, you need to post-process it. And you basically find a high-density solution in your tail solution, and this you can do with another greedy algorithm. Yeah, thanks. Okay. Yeah, I mean, so this is now final slide on the theoretical side. So basically, the nice thing is that if you put all of these pieces together algorithmically, you can still prove a good overall estimation guarantee. So if we have this linear estimation setup, measurements equals data matrix times theta star plus some noise E, under sort of standard assumptions on this data matrix X, you get a quickly converging algorithm, so projected gradient descent, even with approximate projection, still runs in a sort of with a linear convergence rate, and in the end you can recover an estimate theta hat up to this noise level, basically that's inherent in the problem. Again, there are many different ways people in signal processing and statistics set up these types of guarantee. I'd be happy to talk about the technical details later, but I think for now we've had enough theory, so let's look at some experiments. Okay, so sort of let's do the experiment sort of bottom up. In a sense, let's first start at sort of this inner graph algorithmic routine, price collecting Steiner forest. So these are the running times of our algorithm on a set of instances from the 2013 DIMAX challenge. So DIMAX is a theoretical computer science research institute in New Jersey, and every few years they host an algorithms challenge where they say, okay, we want to know what are the state-of-the-art empirical algorithms in a certain area, and then people submit their algorithms and they evaluate them on a set of benchmark instances. And this was great timing for us because in 2014 they did this for Steiner tree problems. So we looked, okay, how fast is our algorithm? And the nice thing is that basically it does scale empirically, sort of nearly linearly with the size of the input. So 300,000 edges, you might say, okay, this is not a lot. Our algorithm only needs 1.5 seconds at most. The one thing to note, which is quite nice, is that sort of all the problem instances they originally had were the ones which are not orange. So the orange instances were instances we added to the competition because on sort of the largest instances they had under the competition, our algorithm ran in a quarter second. So, so to be fair, so our approach to this problem is a bit different. So a lot of the people at this workshop wanted to solve the price collecting Steiner tree problem with the best approximation ratio possible. Since in an NP-hard problem, you can ask, okay, what is the best thing we can do at all? How close can we get to optimum? And our approach was, well, okay, we need to solve this many times, but it's fine if we solve it approximately. So how can we get a provably good approximation as quickly as possible? And then sort of this is our algorithm. compared with other algorithms for this problem. So yeah, this is because we are more sort of in this approximation but very fast regime. So this is an aggregate time measure. We are about 3 orders of magnitude faster than all the other approaches. In terms of solution value, we are about 10% worse. But I think in some regimes, this can be a very attractive trade-off because depending on how noisy your data is, you don't care about the exact solution value, but you can run this very efficiently on large graphs. Okay, so this is on price collecting Steiner forest. So we have code for this. This is fairly polished code actually, so it's a C++ implementation, a Python interface. It does have unit tests, and you can just install this with pip. Good. So the next thing is how I told you about sort of linear estimation problems like compressive sensing, basically recovering a sparse vector from a small number of observations. Let's see if this algorithm also helps there. So what we have here is basically 2 test vectors. So these images is what we want to recover. We can see that they are sparse and that there's some graph structure. I mean, so this is an angiogram. So this is basically someone's blood vessels in someone's brain. And this we submitted this to ICML, so we thought it might be fun to just write ICML and see if the algorithm also works on that. And then you can see, okay, in these graphs, on the x-axis, you have the number of measurements that you need to recover a good estimate. And then the y-axis is the probability of correctly recovering over random trials. And then you see that our algorithm, which is the blue line, does give you the best performance. Sometimes, so the green line, this is a heuristic people had, which is also a very sensible one. Sometimes we're basically as good as the heuristics and sometimes a bit better in terms of statistical performance. And then you can also look at running time. So yeah, I mean, you do pay some overhead. So for instance, the red line here is the same as our algorithm, not without the graph sparsity, but overall it's still scaling quickly. So in particular, what we were trying to beat really was the orange line, which was the prior state-of-the-art and provable algorithms for this. Good, and then going back to the biology problem. So this is sort of preliminary results. When you work with real data, it's really hard to say how well your algorithm does sometimes, because in the end, they're sort of looking for ways to analyze their data and then see whether this is biologically plausible. So what we did was basically experiments with semi-synthetic data. We took a real graph they have, and then real protein expressions data on that real graph. But we added some perturbations to the data that we planted. So we knew what perturbations did we add, sort of which subgraph did we perturb. And then the question was, okay, can we find this perturbation in the subgraph that we planted? And then the answer is that sort of our approach based on graph sparsity gives you a significantly better precision recall trade-off than doing something without a graph structure. So we also have code for that. But this is sort of way more experimental. So if you want to use it, better to talk to me before that. Good. Okay. There are more applications of price collecting Steiner forest. Let's skip that because it's almost lunchtime. So what are the conclusions? So I think sort of, my background is more on the sort of algorithmic theoretical side. So I'm more thinking about, okay, what can we do algorithmically? And I think these are 2 instances where we have algorithms that could work quite well in practice. So we have some evidence that they do work nicely, and I'm curious if there are more applications of this. So the first thing is, as I mentioned, linear regression with graph constraints. So often we want to solve sparse linear regression, and we have additional information about our features that can be represented as a graph. And then the question is, how can you find this most predictive subgraph? So we have algorithms for that. And sort of as a subroutine of that, we also developed fast and sort of rigorously approximate algorithms for price collecting Steiner forest. So given these node prices and edge costs, find basically the nodes that you can pick up so that you get a large amount of node prices, but pay little in terms of edge cost. Yep, okay, and in future directions, I think I'd be very curious if people have ideas for applications. And then more on the theoretical side, a question is sort of what other graph constraints can you impose in regression? So this is all sort of very simple graph constraints in the sense that it's just based on connectivity, but there are more different ways people want structure in graphs, like basically more like how clustered is a graph and so on. It would be interesting if you can also add that on top of linear regression. Cool, thanks.